Hello, this is Professor Kuehn, and welcome back to my lectures on electricity, magnetism, and light. In this lecture, I'll be discussing a student's guide to the Great Physics Text, Volume 3, Chapter 18, which is titled The Particle Theory of Light. You might recall that over the last several lectures, we've been discussing the work of Christian Huygens, who wrote his treatise on light in French in about 1690. In this lecture, we're starting into the work of Isaac Newton. Now, a couple of weeks ago, we started reading Newton's book, Optics, and then we took a digression into Huygens and were introduced to his wave theory of light. Now we're coming back to Newton, and we're going to see how his ideas are very different than those of Huygens. In particular, Newton is going to argue for a particle or a corpuscular theory of light, as he calls it. So you might recall that Newton's book, Optics, was written in his native English language. This is unlike his Principia, perhaps his more famous book, which was written in Latin, and then we read, of course, an English translation. This book, his Optics, was written in English, and so we're not reading a translation, we're reading his direct English verbiage. This book was published in about 1730, and it's structured as a series of queries or questions that Newton is asking, and then Newton's answers to them. So you might think of them as sort of rhetorical questions. He'll ask things like, does not light consist of particles flying from a torch to your eye? And then he'll say, well, yes, of course light consists of particles flying from the torch to your eye, and here's why I think that. So that's kind of the structure that this is going to have. So he's going to argue, as I alluded to a moment ago, he's going to argue that light consists of particles that travel through open space. But the trajectories of these particles, or these corpuscles, as he calls them, can be altered by interaction with substances through which they happen to be passing, such as air or glass, or even Huygens's purported ether. Now, he is going to have some choice things to say about Huygens' ether. He is very skeptical about the existence of ether for a number of reasons he's going to talk about in this chapter. In any case, he's going to develop these ideas in his book, Optics. So let's go ahead and take a look at query number 25. That is where we're going to pick up this work of Newton. And in this query, he begins by asking, what are the properties of light rays? Now, you might remember when we started reading his Optics a little while back, he talked about light rays as being the thinnest possible sliver or pencil, he might say, of light that comes through a region of space. So he already has articulated what he believed were some of the most important aspects of light rays, namely the law of reflection and the law of refraction. And here in query 25, he says, are there any other properties that these light rays have besides traveling in straight lines and being very, very thin like geometrical lines? And one of the answers that he gives is that they have a unique and interesting property, which is illustrated or perhaps suggested by their refraction when passing through a very unique substance called Iceland Crystal. Iceland Crystal, I have a piece of it right here. You might not be able to see this very well over my webcam. It is a parallel pipette kind of crystal structure. It's beautiful. It's kind of, it's translucent, so you can see through it. It's transparent, and it has these cleavage planes that are at these kind of funny angles, so it breaks naturally in this shape. It's called Iceland Crystal, presumably because it was found at first in Iceland, and it's also called calcite. Sometimes in the writings it's also called island spar. Okay, so he's going to point out that when you pass light through this Iceland crystal, which was first studied by Erasmus Bartholinus, he says, and also by Huygens, he noticed that it has this interesting behavior. That is, it is birefringent. So he says if you take this crystal and you set it on top of a book and look through the crystal at the letters that are beneath it, there will be two images of each letter. This is something you're going to be looking at in lab this week. And these two images of the letter that you see are going to be about equal in color and brightness to one another. He also mentions that a beam of light that you pass through this crystal is divided into two separate beams. One of these beams obeys the ordinary law of refraction, that is, the sine of the angle of incidence divided by the sine of angle of refraction is about 5 to 3. So there's a constant ratio of these signs of the angles of incidence and refraction. So if you pass a light beam into this crystal, there are two separate beams that are created. One of them experiences ordinary refraction. He calls this the ordinary beam. But there's another beam that does not obey Snell's law. In particular, he calls this the extraordinary beam. So if we look at page 211 in the text, he has a schematic diagram depicting a crystal of this Iceland spar or calcite. And he tries to describe in great detail the various angles between the faces of this crystal. And what he's pointing out in particular in this diagram is that if you have a beam of light entering it from the top, and this is denoted by the line ST, when it enters the crystal, it will be divided into two separate beams. One of them will pass along the line TV, and he says this is the ordinary beam that obeys the ordinary law of refraction. There's another beam, TX, that is the extraordinary beam that does not obey Snell's law. So let me explain in a little bit more detail. I'm not going to read through this for you. You can read through it on your own, and he provides a bit more detailed explanation. But perhaps the thing that most clearly illustrates why this does not obey, why this is a unique crystal, is if we consider this. So I'm going to draw a picture. Oops, let me get a different color here. I'm going to draw this crystal, and I'm not going to draw it in 3 dimensions like he does. I'm just going to draw a block of it like this. I'm not going to worry about the angles for the moment. And he mentions if you were to have a beam of light coming from the top, and I'm going to make this a red beam of light. I'm reading at the bottom of page 211. If you have a beam that comes in perpendicularly to the top, like this, well, what you'd expect when you have a beam coming in perpendicular to the surface is you'd have the beam going straight in, right? So that obeys sine of theta incidence over sine of theta refracted equals a constant. Well, the angle of incidence is going to be 0, and the angle of refraction is also going to be 0. Okay, so if the angle of incidence is 0, the angle of refraction is going to have to be equal to 0 as well. And so this is what you would expect, and sure enough, you do have this ordinary beam that does this. However, you have this extraordinary beam as well that is broken off and goes to the side. And he says that the angle right here between the extraordinary beam and the ordinary beam is 6 degrees and 40 minutes, or 6 degrees and 6, I guess we'll go back for a second. He says it is 6 2/3 of a degree, because 40 minutes is 2/3 of a degree. Okay, and he says that as these beams travel through, when they get to the other side, once again they'll obey the same law of refraction. So this one will go through straight like this. This one, when it hits the side, it will then bend once again, and it will come through like this. And so the outgoing beams will be parallel to one another, but offset from one another. This is the extraordinary beam. Okay. So that is what he's highlighting here on page 210 and 211. This is a very peculiar kind of thing. Okay, and now what he's going to do is he's going to say that if we do this again, but we take the ordinary and extraordinary beams and pass each of those through a piece of crystal, we see something else interesting happen. So I'm going to draw a diagram once again. Suppose we have a piece of this Iceland spar. I'll draw it like this. And again, I'm not going to pay attention to getting the angles exactly right. But if we have a beam of light coming into this Iceland spar, it will be broken into these two beams, like this and this. We'll call this the ordinary beam, or O, and this the extraordinary beam, like this. And he says, now if you were to take these two beams and pass them once again through different pieces of Iceland spar that were oriented in the exact same way as the original piece of Iceland spar, then the ordinary beam which goes into this one would refract once again in the ordinary direction. It would behave like an ordinary beam, and this extraordinary beam and going through here would refract in the way the extraordinary beam does when passing through a calcite crystal. So it doesn't further divide these. So this is another experiment that is of interest. This experiment right here, okay? Okay, so how is he going to try to understand this behavior? Okay, he has a few more variations on this experiment. Maybe I'll talk about those in a few minutes. But what he speculates, he asks there, he says, this is about the middle of page 212. He says, and therefore there is an original difference in the rays of light, by means of which some rays are in this experiment constantly refracted after the usual manner, and others constantly after the unusual manner. Okay, so he says there is an original difference that exists in this ray of light. What does he mean there? He's saying that this original ray of light that is coming into the Iceland crystal, it has some property that allows the crystal to divide it into two separate beams. So there must be some feature of that original beam that the Iceland crystal can select between. And he starts talking about how perhaps the beam has some kind of orientations to it. So you might think about it this way. Suppose this original beam consisted of, if you looked at it on a microscopic level, suppose it consisted of tiny particles. This is eventually what he's going to argue. But instead of these particles being spherical particles, consider them to be ellipsoidal particles. And these ellipsoids can be oriented either sideways or up and down. And they're all flying in this direction. So if that's the case, then you would have, when they strike the Iceland crystal could in some way select between these two kinds of orientations, or as he calls them, polarities of the beam. Perhaps the ones that are oriented in the horizontal direction would fly off in one direction, and the ones that are oriented in the vertical direction would fly off in another direction. So in other words, he's arguing that there is some property or some sidedness to this beam that the crystal can select between. After all, if there was no sidedness or different kinds of particles, the crystal would have nothing to select between. It's kind of like if you have a shepherd and he wants to decide between the sheep and the goats, there have to be different kinds of animals, sheep and goats, so that he can divide them between sheep on the one hand and goats on the other hand. So there have to be two different kinds of things that the shepherd can divide between in order to produce two different rows of animals. Likewise, if the crystal is going to produce two different beams, there must be some feature of these particles that it can distinguish between. That is where Newton is going with this, and I'll pick up this discussion more next time.